Experiential. You can learn about drinking in the classroom, but it's never real until you put it into action yourself.
Okay, attitude. You can sit in the corner. Please try to do all. Where does that end up?
Yeah. Well, I just didn't test it.
Oh, dude, I forgot my wedding room down there. I was like, hey, did you survive our days? He's like, yeah. I was like, I'm sorry I didn't check yesterday. He's like, yeah, I think it's good.
Is this Richmond good?
This is my Facebook. Okay.
If you want us to do this.
Yeah, I thought about making it a little bit, but it's also got plugs underneath it.
The rug is keeps it from being heavy.
We'll wait a couple minutes. Last minute, get some snacks. No, I'm not waiting on you guys. We got people who are going to trip
Are you
in.
attacking us right now?
Jesus, Kylie. It's always you.
I'm trying to hustle. I'm hungry.
I had a good one today. I was scrubbing one kettle brushes and get split. I said, yeah, it's like trying to drown a fat kid. You can pull him down, but he's going to fall right back up. It's like, I was like, yeah, we're going for it. It's also like using like your mouth, your like singles.
No, we're still anywhere, so it always says that.
How's physics going?
Good.
You have a good
January.
Yeah.
I just dropped my work.
Five and six. So I have to build it. I should be able to build it. Yeah, and you want to teach me her.
I'll try to introduce you.
Yeah, I guess as long as it takes
I think those. Why?
Yeah, maybe.
Because they have the money. I don't mind the concert. Oh, I'm actually.
People prefer that as 100% of their training. Training other than or
Exactly, because they have to.
As soon as you like want to keep it landed, you don't want to do any further around.
Exactly, you want to run as minimal land.
Does anyone know where the light switches are?
Yeah, they're right there, bud.
No, I don't think these are for them. Yeah,
Is that the light switch over
Just
there?
that one single.
I didn't see anything either. Michelle, where are the light switches? No, those are not light switches. Sun's out. Oh,
But you want it that way? There seems to be only two options.
yeah, how do we turn off just the front row? I feel like it has happened. Yeah, that's dogs. Yeah. Oh, good.
Yeah, just let us.
Oh, there we go.
Where the problems are. It's okay, I'd rather be in the dark than in the light. No worries.
Okay. Sweet.
There we go.
Cool.
Does that look good?
Yeah, that looks nice, thank you.
Alrighty. So, oh, thanks for coming, folks. So we have a guest speaker, Kimberly DeLong, or Beryl to her friends, and she is visiting us from UC Santa Cruz, where she is a PhD candidate. She is an adjunct here for 2 classes. Currently, she's teaching oceanography, which might be the first time and maybe the only time oceanography will ever be taught at Western. And she'll be teaching chemistry later in Block 4. She earned her bachelor's in geology, right, from UNC Chapel Hill in 2012, and then a master's in oceanography from University of New Hampshire in 2015. And she's now pretty close to finishing her PhD. So I guess with that, I'll let Beryl take it away.
Okay, thank you, Neil. All right, so I was asked to give this talk and I came up with the vaguest possible title. I'm going to try to spend a decent amount of time on background since I know most of you guys don't work on the ocean. So the sort of takeaway theme is that ocean fossils can reveal a lot about extreme climate events of the past. Didn't want to muddy it up with which climate events we'll be looking at, or which fossils for that matter. But yeah, so what do I mean by extreme events? Extreme events can kind of be visually shown by this sort of graph. So I didn't put numbers on it, but you can just kind of see for the most part, climate is going to be controlled by the amount of solar radiation coming in from the sun, insolation. And we can model that we can calculate that really clearly. It's like these gentle sort of sine waves, the amount of solar radiation. Oh God, I didn't realize that would write on it.
Oh God, yeah. Enjoy the next 30 minutes of hell.
Should I just leave it there?
Yeah. It'll go away. No touchy.
Oh, is that gonna
Yeah.
go? Is that gonna go away?
It doesn't
No.
go away?
You tap it, there should be.
Yeah. There you go.
Oh. Okay, didn't realize that was live. Thank you. Okay. Anyways, these sort of gentle sine waves show the changing amount of solar radiation coming into the Earth. That's a first order control on Earth's climate. But this sort of white line is showing an ice core record from the Northern Hemisphere, which is thought to be a very faithful record of regional climate in the Northern Hemisphere. And this is insolation at 65 degrees north. So they're from around the same location. But you can see Earth's climate, it sort of follows insolation in a general sense, but it's punctuated by these really, really extreme, rapid, much shorter term events that are really, really high in magnitude. So this is showing the last ice age. And then this is the warming into the like more warm, stable Holocene that we're all living in and more familiar with. Some of these changes of rapid warming and then rapid cooling are almost on the same scale as the entire change from an ice age to a warm period. So that's what I mean by an extreme event. They are very sudden, they seem to be unpredictable in their timing, and they have a really large impact on regional climate. So what I'll specifically be looking at for this talk is the deglaciation. So that warming from glacial times to like more modern warm times. That's called the deglaciation when we're like moving out of a glacial time. We would expect warming because of this increasing insolation, but it seems that it was a really bumpy ride on the way there. So we have this period of really, really sharp warming, and then a period of really sharp cooling, return to glacial-like conditions, and then a period of really sharp warming again on the way to our interglacial or warm period now. So what's interesting about these kinds of extreme events, if you just plug in the things that we know, for example, changing insolation is going to change the temperature of the Earth. That temperature might change a little bit more in different places over continents versus oceans. That could change the winds, that could change ocean circulation. These kinds of physical parameters of the climate system we can model, but those physical models don't seem to be able to reproduce these kinds of extreme rapid events. So we know that there has to be something else going on that's internal to the feedback system, that's internal to Earth's climate system. It's not coming from the outside like the sun. That would be an external input. Instead, it's just something going on Earth's surface and presumably for a lot of it in the oceans. So that's kind of why I'm studying this particular event. So this is that same ice core record, but I've just zoomed in on the deglaciation only. So this is the last glacial maximum, the early part of the deglaciation. This really rapid warming is known as the Bowling and Allerod, or just Bowling Allerod. You often just smash those together. The Younger Dryas is this cold period, warming again in the pre-boreal before we get to the Holocene. So now I've just put the numbers on there. This is a ice core from Greenland, but it's pretty representative of the entire Northern Hemisphere and a very faithful recorder of Northern Hemisphere temperature. And while studying this sort of deglaciation and the Bowling Allerod, this like really sharp event, a lot of people, not me, like this has been something that's been noticed by scientists for a lot of years, but in the subpolar part of the North Pacific, which I'll define in a second, the amount of primary productivity or the amount of phytoplankton or algae that are growing there, forming the base of the food web there, was really, really low during glacial times. Huge spike, like lots and lots of productivity during the Bowling Allerod, and then goes back down to sort of low levels that we are more familiar with today. So there was a thought when looking at these, and this is like throughout the entire region of the North Pacific, could this be one of those internal feedback mechanisms that's helping to amplify changes in insolation or spread or like pass along to different parts of the climate system some kind of signal, forming some kind of positive feedback loop or negative feedback loop on global climate. So why we care so much about algae and marine phytoplankton, they mediate a lot of the carbon that's in the global climate system. So most carbon that's active in the ocean and atmosphere is stored in the deep ocean. And when I say most, I mean like most by a lot. So these squares kind of represent how much carbon is in these different reservoirs. There's not very much in rivers. There's a lot in the atmosphere. There's a lot in the ocean surface. But if you could move carbon dioxide from the atmosphere to the deep ocean, it might stay there for a really long time and get stored. Or if you could move carbon from the deep ocean back into the atmosphere, you could release CO2. Maybe that would help Earth warm up even further. So that is a really potential feedback mechanism on like a global scale for all kinds of climate events. But for marine phytoplankton, if they are, for example, growing a lot in the surface, they could be grabbing all of that CO2 from the surface and exporting it to depth while their bodies sink. That is known as the biological carbon pump. This is just a super simple visualization for you. When phytoplankton grow, they're using carbon to grow. When their bodies die, it sinks to the bottom of the ocean and it gets turned back into CO2 in the deep ocean. So that's one way that phytoplankton can sequester carbon out of the atmosphere. So there's sort of an idea, if marine phytoplankton were going to be controlling global climate, theoretically, there's other things going on, but this aspect of global climate, if you had more primary production, more algae growth, you would draw down CO2 that could induce a cold period like an ice age. Or if you had less primary production, you would have excess CO2 left in the surface to equilibrate to the atmosphere, and that could lead you into a warm period. What I will mention is that that primary production by those phytoplankton is actually controlled by which nutrients the phytoplankton need to grow. So that is why I study nutrients. It's kind of a few steps backwards in the whole system. But basically, if you're controlling the nutrients, you're controlling the phytoplankton growth. Maybe that's controlling this carbon cycling. So this is some famous work that shows the possibility that phytoplankton really could be playing a super active role in carbon sequestration. It's the idea of iron fertilization. And the idea has been kicking around for a really long time, but this study showed that it's actually really possible and probably has been happening in the past and really influencing climate cycling. So this is not where I'm studying, but it's just like a beautiful example of what we mean when we're looking at nutrients affecting phytoplankton growth. They went to this one site in the middle of the ocean. I did not touch the screen too close. Where it receives variable amount of dust from the Atacama Desert. So if you're in a dry period, you can have lots and lots of dust going and reaching that site, and that dust is delivering lots of iron. So if you're in like a cold, dry period, you could get tons of dust there. And if you're in a warm period, this place would get more plants, more wet, less dust, and you'd get less iron getting delivered to your phytoplankton. Iron being a nutrient that would stimulate phytoplankton growth. So they went there, they measured the amount of dust, they measured the amount of iron. It's almost the same because that's the main source of iron here. This is temperature from the southern, from like an ice core that's in Antarctica. So this is a southern hemisphere now, but I just wanted to show it because they claim that this is like one of the major drivers of CO2 changes in the past. This is during the last glacial period. And they looked at the nutrient utilization as a way to measure what was happening with the phytoplankton. So in this case, they picked nitrogen as their nutrient. And they found, I'm not going to explain delta notation, but anyways, these higher values of N15 is showing more nitrogens getting used by the phytoplankton when they have more iron. So the iron is fertilizing them. They're able to use more of the nitrogen that's available to them, and that's causing them to grow a whole lot, sequester tons of CO2, and move the southern hemisphere basically in and out of these temperature swings by regulating the CO2 in the atmosphere. So Okay, that guy's a genius. That was like a beautiful study. It works super well. It shows that this is really possible. So everyone else now is starting to think, okay, where are other places in the globe where we could check if iron fertilization is something that's really going on? Is this only happening in this one part of the Southern Ocean, or is it also maybe happening in the Northern Hemisphere? So I'm going back to the Northern Hemisphere for the rest of the talk, but that's kind of the same signal or hypothesis that I might be looking for. Okay, I think I just showed you this. I'm not sure I wanted to say anything else about that, but we're just going back to the Northern Hemisphere. Okay, to define the subpolar North Pacific or the region that I'm studying, I picked a core site here. So when we take these ocean cores, we go out on a ship and drill some sediment, and yeah, we're just reconstructing the changes in environment that were occurring at that location. Then I have it plotted here with the amount of nitrate in the surface, which is another that nitrogen nutrient, and silica in the surface, which is another nutrient for phytoplankton that make their shells out of glass. And you can see by these kind of colors, purple and red, those high values of nitrogen and silica in the surface are sort of unusual in the ocean. Usually when you have lots of nutrients like that, you would just have the phytoplankton use them all up and take them down to zero. So the fact that there's all of this extra silica and extra nitrate in the surface water is telling us that this is a place that's probably limited by some other nutrient, in this case, iron. So we're looking for a place where if iron is limiting growth, like they have all the nitrogen they need, they have all the silica they need, they're just waiting for some iron to grow. This would be a place where iron fertilization would be possible. All you have to do is sprinkle some dust on top or a different source of iron, then they would have all of the nutrients they need to grow and they would be able to bloom. Okay, so there's a thought, I guess, when looking at this, there's this huge change in productivity through the deglaciation. There's the thought to anyone who's familiar with this region of the ocean, the subpolar part of the North Pacific, is maybe this could be a site where iron fertilization is happening. Maybe all that happened is you added extra iron during this unusually warm period or this extreme event, and maybe that stimulated phytoplankton growth just briefly here. This would be a good place that you might think iron fertilization was possible. Okay, but there's actually a second thing going on that partly explains these high nutrients. Unfortunately, it's not quite as simple as iron being the only thing limiting growth. So there is a very low iron supply, and that is going to chronically limit the growth of really large diatoms, phytoplankton that need lots of iron to grow. But there's also a really permanent halocline, or sort of freshwater, it's not freshwater, it's ocean water, but a lot fresher surface water that's really stable here in the North Pacific. So this is a transect showing salinity with depth. Here's my core site, and I'm showing how deep it is, but that's not so relevant. So this is just showing throughout the whole North Pacific, there's this layer of surface water that's just always going to be stably sitting on top of the deep water. And that's going to prevent really deep mixing in winter. So we call that a permanent halocline when there's always that kind of fresher water on top. And that means every spring, zooplankton are really poised to graze down any phytoplankton that grow. Here's sort of what the production of the subarctic Pacific looks like. Through the year, it's kind of small, whereas zooplankton can grow massively in the summer. So I'll just contrast that to the subarctic Atlantic. In the Atlantic, they have really, really deep mixing. They don't have that permanent halocline. So when you have in spring, there's more sunlight, the phytoplankton start growing, the zooplankton are hibernating for the winter. So the phytoplankton can start growing in the spring. They'll just bloom and bloom and bloom until the zooplankton have reproduced enough to start blooming themselves. So there's like an offset between the spring bloom of the phytoplankton and when you get zooplankton grazing that down. Okay, and then there's sometimes like a little fall bloom after the zooplankton go to sleep for the winter when phytoplankton can kind of keep growing. So actually what's happening is phytoplankton are growing this whole time. It's just the zooplankton are grazing them down. So that's why it looks like there's less in summer. And it's the same thing here. Actually, maybe I'll draw on the board. Okay, I don't know.
Maybe try those markers that are at the bottom.
Cool. Okay. Basically, the phytoplankton are growing that whole time in summer. It's just the zooplankton are grazing them so efficiently that the zooplankton are the only thing around when you go to measure it, and the phytoplankton are always kind of at these lower values. They're just being grazed as fast as they can bloom. Okay. That works so well. All right, so both of those are causing there to be excess surface nutrients at this location. So we have to consider both explanations, both iron and changes in this sort of depth of the mixing based on the halocline if we're looking at this event. So that's going to lead us to two different hypotheses, but I'll focus on iron first. This is a paper from way back in 2013, so I'm obviously not the first person to investigate this. They went out to a really nearby location, so this like really nearby location, and they said, I'll just measure all the iron that's there. And they did really, really careful chemistry, and they divided it up into like volcanic iron versus dust iron to find if there was extra iron getting inputted during the Bowling Alrod. I forgot to say the Bowling Alrod is always going to be like these yellow lines here and the pre-boreal there. Okay, anyways, this is where we'd be looking for like a huge spike of iron if there was extra dust there, but they didn't find any. Instead, they found, so these two added together make this kind of upper one. There was just a lot more iron in the glacial times, and there's just sort of a gradual taper off of the iron supply going into the Holocene. There was no huge spike. So to some people, that kind of set the idea to rest. But there's a sort of secondary source of iron that could be in our system, and that is flooding the continental shelf. So here in gray, you can kind of see there's a huge continental shelf in the Bering Sea, and that could be a different source of iron other than dust. Okay, so in the last glacial period, sea levels were a lot lower. That all of these continental shelves were pretty much not covered by ocean water. So iron sourced from sediments on the shelf, as instead of dust, you can just like have some iron being leached out of sediments on continental shelves and going into the ocean that way. Here's modern estimates of how much iron is coming from continental shelves. It's quite a lot, especially in this region. But that during the last glacial period, that wouldn't have been available until you had meltwater from all of the ice sheets that are around during ice ages. They melted really rapidly, and they caused sea levels to rise really rapidly. And that happened in two pulses. And the pulses are the Bowling Alrod and the pre-boreal. So the timing is exactly right for this. So the idea is maybe you had these meltwater pulses, the ice sheets are collapsing really, really rapidly, continental shelves are getting flooded really rapidly. That could be the way that iron got out there instead of dust. Okay, so the meltwater pulses, they're called 1A and 1B. That's just in case you've heard of them before. But the idea is you just have these sources, potential source of iron as meltwater's flooding continental shelves. But here's the second hypothesis, and so this has to do with changes in the degree of vertical mixing. Maybe there was upwelling and downwelling, well, no, upwelling and deep winter mixing going on, disrupting that sort of halocline and changing basically the entire structure of the ecosystem. Okay, so why we think that? I mean, it's kind of it's much more crazy of a hypothesis because there's not a super strong mechanism to explain how this would be happening. But this study, Gray et al., they went out to, again, really close to these last couple of core sites, and they measured the flux of CO2 in the surface. They reconstruct this from boron isotopes in floating plankton shells. of 4 Okay, so they did this really careful chemistry on the isotopes of boron. They have a pH reconstruction that they can do with that, and they can see, was there a lot of CO2 in the surface water there, or wasn't there? And it's a difficult measurement to make, so they don't have a ton of data points, but they basically found during the Bowling-Allarod, when we had that productivity spike, there was actually more CO2 in the surface ocean than before. Okay, so to bring it back, the phytoplankton, you would think if there's tons and tons of phytoplankton growing, they would be drawing down the CO2 in the surface. Every time they grow, they're taking up carbon, and this productivity spike is a huge carbon burial event, right? Like every phytoplankton or algae that grows, a lot of them sink to the bottom. They get captured in the sediments. That's why we have this opal spike. They're burying carbon. They should be pulling carbon out of the atmosphere through that biological pump mechanism. But despite this really high carbon burial event, this group found that CO2 was actually leaving the surface ocean, exhaling kind of. The whole ocean was providing like a source of CO2 to the atmosphere. Really opposite to what you might expect. If you were releasing carbon dioxide from the deep ocean to the atmosphere, that would have contributed to more CO2 in the atmosphere and more warming in that deglacial period. So we've got two really opposite hypotheses to explain what's going on here. And luckily for us, they are so different from each other that it's going to be kind of easy to test. Inherently, this is suggesting really, really different circulation of the ocean is going on. So this is suggesting really, really deep mixing is going on. A total breakdown of that permanent halocline, which no one was really expecting. It would be really difficult to explain how that would happen. You would have to basically remove intermediate water formation. It just seems really confusing, and no one's really sure, like, no one thinks that that would have happened in the ocean. Well, they do now, but anyways, when it's first getting proposed, it's kind of like, how could that happen? The mechanism is still super unclear. On the other hand, this mechanism makes perfect sense. We know that the continental shelves got flooded really rapidly. These meltwater pulses are very well constrained by all kinds of different climate proxies. And you would think that meltwater, if you're introducing tons of fresh water to the Pacific, you'd think that would stratify the ocean further. You'd think that would cause more fresh water in that surface and prevent deep mixing. So we're having like completely opposed propositions here to explain that that high productivity. Actually, I didn't even explain how that would cause high productivity, but the idea with this one is if you have deep mixing, you're bringing lots and lots of nutrients to the surface, and you're probably doing it seasonally. So I'm calling it seasonal upwelling. Just to go back, we would be proposing that there's some kind of deep mixing, changing the whole ecosystem to look more like the Atlantic. So this is a place where you have that seasonal signal, which I'm going to call seasonal upwelling, but it's going along with like a deep mixing of the ocean scheme. Okay, so now that you know our two hypotheses, I can show you the approach that I took to kind of test and find out what was going on. So the proxy I went for is Delta 30 silica. I didn't really explain on here exactly how it works because I feel like you can get bogged down on it. So anyways, just trust me. But it's a nutrient. So just like that nitrogen nutrient that other study was looking for, we went with silica instead of nitrogen because nitrogen has some extra caveats to it. It can change from different reasons. But silica, it's pretty much only going to be changing based on how much the phytoplankton are taking up of that nutrient. So I isolated some diatoms. Here's a picture of what my samples look like. Luckily for me, there's some really, really large diatoms that are available throughout the entire time series that are just a single genus and mostly a single species of Cossinodiscus. It was really easy to isolate them and just get the silica and then take the isotopes of the silica to see kind of the nutrient status of those diatoms. It's kind of a late summer, fall bloomer, but it kind of blooms all summer, especially during the fall bloom. Okay, so delta 30 silica is a direct proxy for the utilization of silica, how much of that nutrient silica is getting used. And that's just a ratio between how much is getting uptaken by the phytoplankton versus how much of supply of that nutrient is around. Basically, these different isotopes, the phytoplankton would prefer to use the lighter isotope, which is 28 silica. They only use 30 silica if they have to, if they're running out of silica. So the amount of 30 silica that's incorporated into their shell is telling you, were they being really choosy about the silica, or were they more starved for silica and using any silica that they could? So that's inherent, that utilization is inherent to just the 30 silica, but I have a second proxy that's kind of a rough approximation of how much that uptake was. So I have the flux of diatom opal to the sediments. It's literally, I'm just counting the amount of diatoms that are in the sediments. So the flux of their valves are their shells. So it's a direct measure of primary production. Okay, and then because we have the utilization known from the delta 30 silica, we have the uptake known, we can actually rearrange that and calculate what was the supply of silica to the system, since these two, I have direct proxies for those two ones. Oh, okay, so we can apply those to our hypotheses. If iron addition was sparking the productivity, the utilization of silica should increase. We're assuming that they took up way more silica because they're growing and growing and growing, but the supply of silica didn't change, just the iron is spurring their growth. Versus if there was a change in the supply, which deep mixing of the ocean or huge changes in the seasonality of the system or changes in intermediate water, that would bring more silica to the surface if you're having deep mixing. So if we calculate supply, we can just sort of directly check how much silica was available to the phytoplankton by mixing. Okay, so here are my results. We're basically going to spend the rest of the talk on these figures. So at the top, here's my diatom valve flux, which is a measure of productivity. It's actually on a log scale. There was a really huge change in productivity. So here's the bowling alley rod in those yellow bars, the pre-boreal, and you can see we've recorded that productivity spike really clearly, like we expected from all the other studies in that region. Definitely showing the peaks where we expect them. The timing is really well constrained, where the beginning of all of those events are, so we can be confident in our time scale as well. And then here, this is just another sort of check on, do we have the timing right? I have the 018 of some planktic floriums. It's just a measure of basically the density of surface water. So I have it plotted backwards. The lighter values are up. So this is telling you less dense surface water, saltier or colder surface water if it's going down. So we can kind of see there's actually more extreme changes at the beginning of the deglaciation than we would expect. But you can see there's a little bit of warming and freshening going on with the meltwater pulse. That makes sense. We knew regionally that was a really warm period with that spike in the ice cores. There's meltwater, so we expect it to be like a warmer and fresher time, a little even more extreme towards the end of the bowling, a little bit saltier in the younger Dryas, or colder, probably colder, and then we were going into the Holocene. So those, I mean, this is really just like a check that we are in a place that's like accurately recording these signals. And the productivity we're going to use as our uptake in a second. Oh, no, right now. Okay, so here's the delta 30 silica of Casinodiscus. That's our utilization signal. Those are all of the data points that I generated. And then we can take this calculation. We know that that's a direct proxy for utilization. I actually had to plug in a lot of values that I took off of here because I thought it was too complicated. But I'm changing that based on the species and the things that we know about the species into a utilization. And then we know it's a ratio between uptake and supply. So I'm plugging in productivity here from my diatom flux as the uptake. I decided to take the log because otherwise it was like too extreme. Diatom valve flux is a little bit of a self-reinforcing proxy. The more diatoms you have in the sediment, the even better that they preserve. So anyways, I decided to take the log of that, and you divide by the log of uptake. I guess I should have put that in green. That's just the diatom valve flux divided by the utilization, and we can calculate the supply. This is the same formula I just showed on the last slide, but the purple is my calculated relative supply. Oh, I also normalized it all, setting the LGM, the last glacial maximum, equal to 1. Because this is just a really, really, it's a very calculated, and it's really only a relative measure of supply. It's not going to tell us like, oh, there was exactly this many moles or something. It's just sort of a way that you can see like the relative changes between the green line and the blue line. So everything that I'm telling you about supply, you could in your mind, like just look at the uptake and the utilization, do like a little calculation in your head and get this. But I just wanted to put it up here because visually it's nicer to see. So I set the LGM equal to 1, and these are all the relative changes relative to what the last glacial maximum value was. Okay, so this is just a reminder on how to interpret the silicon isotopes. If you have really high delta 30 silica at the same time that you have low productivity, those are times that they might be running out of silica. They're using more of the 30 silica, which is the one that they dislike using, and productivity is still not that high. So the only times where that seems to be happening is maybe this random event, but it's just this one kind of weird data point, so we're not even sure that that's super trustworthy. Or here at the end of the pre-boreal, you have productivity really falling, and at the same time you have silica use really increasing. That's telling you they're running out of silica. They're not even growing that much, and yet they're using a lot more of the silica 30. So that would be the time that the supply would be the lowest. And likewise, if you have low 30 silica, they have all the 28 silicas that they want when productive. Oh, and with, okay, whether the productivity is high or low, that kind of applies to the utilization. But especially with low productivity, that would be a time of like excess silica. So this is our lowest 30 silica that we measured. Also kind of a weird anomalously low one, but that is why the supply calculation shows a little spike there. Productivity is really low. 30 silica is also really low. There's just extra silica. That's what the calculation is showing us. Okay, so now we know how to read it, and what's my interpretation? Well, I found my productivity increased by something crazy like, well, the diatom valve flux is like 100-fold. Really, I also did opal measurements, and it's more like 10-fold in the opal, but basically an entire order of magnitude more productivity. It did not seem to induce any silica stress at all during the bulk of this high productivity event. I mean, the 30 silica goes up a little, but really it just goes back down to like very similar values as is going on in the early part of the deglaciation. So that's really the main conclusion or finding here is, silica increased, the silica utilization of the silica increased a little bit, but the productivity increased just so much more. It increased like 10 times more without inducing very high values in the 30 silica. By the way, these numbers on 30 silica are all between 1.1 and 1.9, but it can get over 2 if they're really, really stressed for silica. So really at no point on this record are they really showing extreme silica stress. They could go up to like 2 or 2.5. So really there's very, very moderate changes in silica usage when you have like these 10-fold changes in productivity. So that's why this calculation on supply is showing, okay, silica supply must have just gone up. And my calculation shows that it just a little bit less than double the amount of silica supply. compared to the LDM. So that is really strong support for that seasonal upwelling hypothesis. We would have expected a huge spike in 30 silica if iron fertilization was driving things. This seems to show instead you had deep vertical mixing, bringing just tons and tons of nutrients through mixing alone to the surface. So, okay. On top of that, though, we can look in a little bit more detail. A small increase in 30 silica does seem to be happening, especially at the beginning of that event. So there is a little bit more of the available silica pool used. It's just the silica pool maybe doubled. And then on top of that, a little bit more percentage-wise was being used. So there are a lot of other factors that can affect productivity. It could be iron from flooding continental shelves is part of that equation. But there's also changes in light availability since the stratification is changing. The depth of mixing is going to potentially be changing a lot. The seasonality of it is changing a lot, changing the amount of zooplankton grazing, and even changing temperature. We know it was a warm event and warming. So all of those things are probably going into the change in the available, the change in how much silica was being used by the system. We can't really say one way or another, like which of these is having the biggest secondary effect. So it's not goodbye to the iron hypothesis, especially just for those first two where it really does seem to show an initial increase in silica utilization. It still could be that maybe iron supply was particularly high during that meltwater pulse. But if we're looking at an idea of lots and lots of deep vertical mixing, that's suggesting a huge reorganization in the ocean circulation. So we have to also consider if you're bringing some kind of huge amount of old, deeply sequestered CO2 and carbon to the surface, maybe you're bringing old sequestered silica to the surface at the same time. Maybe actually the isotopic value of that deep vertically supplied silica, maybe it's just a little bit different than what like all of my calculations are assuming that the isotopic signature of silica is controlled only by the phytoplankton growth, not by the preformed value that's showing up at the beginning. So there is a sort of paper that's hypothesizing if you're having huge reorganizations in ocean circulation, you might be changing your isotopic signature. So it's also possible that that could be going into it as well. But one thing we can say about iron is, from the other study, we know iron supply from dust is like slowly decreasing through time. It does sort of seem like at the end of the pre-boreal and going into the Holocene, we have this other increase in supply. So leaving the bowling Allerod alone for a second, productivity is sort of gradually increasing in the Holocene, but silica utilization is going down, really down. So that's why supply seems like it kind of climbs a little bit. This could be the onset of iron limitation in the region. Individual cells sometimes use more silica if they are iron limited, but remember what we saw at the beginning. Now that it's an iron limited system, there's just tons and tons of excess silica available all the time for diatoms to use. So the community as a whole is encountering excess silica if iron is limiting them and silica is not limiting them. That could be why silica supply sort of appears to go up. Maybe this is the onset of iron limitation. They can be as choosy as they want with their silica now because they are waiting on iron. They have all the silica that they need. Okay, and then I just threw this in here because, how are we on time? Can you give me an update?
It's 4:45.
Oh, so wrap it up, right? Okay. Well, I just.
Take another 5 if you want.
Oh yeah, no, this is the conclusion. I just was going to show a couple other things because I don't know. There's more than one way to answer the question. It doesn't have to be only from like strictly geochemical proxies. So you can just look at which diatoms are there, which phytoplankton are there. They're leaving their glass shells behind. You can just do a community analysis. So we have one specific species of Chitoceras. It is an indicator of upwelling. It's an indicator of a lot of different things, but upwelling or high productivity times is sort of like when it thrives. And you can see there's sort of, I'm not really sure what this little short event is, but basically the Chytoceras, it becomes a huge part of the community during this high productivity event here. Meanwhile, we have a different species of diatom, Rhizoselenia, which is very common during the Holocene, but it's basically not common at all during this high productivity event. So it seems like that is another indication that you just had a very, very different community structure. It seems like it supported diatoms that are more common in upwelling areas or spring bloom events. You could think of it like spring bloom events instead of the one that's more common now, which thrives in stratified waters. So that's just further evidence. And up here, I have a proxy for ice rafted debris, which is sort of like another check on how cold it was or something. It really seems to be showing that during those cold, regionally cold periods, you just have lots of ice rafting. You have a little bit more of the stratification indicator. Even on these short-term events, the cold periods seem to be really stratified, but that warm period, the Boulign-Allarad and the Pre-Boreal, are more marked by upwelling and less marked by the stratification indicator. So just another way to kind of check our conclusion. Okay, so our conclusion is there seems to be seasonal upwelling during the Boulign-Allarad, or moderate and decreasing 30 silica during really, really high productivity. Is just showing that there must have been a lot higher supply of silica to that region. Lending support to that hypothesis that there was really, really deep mixing of the ocean and seasonal upwelling. So I have here, instead of labeling this as the Atlantic, maybe during the Boulign-Allarad, the subarctic Pacific didn't look like its modern stratified zooplankton grazing kind of community. Instead, it looks like they had really strong spring blooms, a lot deeper mixing in the winter. Zooplankton are hibernating, so you can get more of this like spring bloom, extreme carbon burial events. Okay, just skip that. Okay, and that's all. That's my conclusion. So I can take any questions. I don't know. You can mediate. Does anyone have any questions?
Rob, looks like you going?
I think so. So, upwelling's being driven by cold. Is it assumed that the upwelling's being driven by cold water currents on the bottom that are then being ramped up the slope edge, bringing those nutrients up and causing those blooms?
This would be upwelling that's really wind-driven more. So the hypothesis that the Gray et al. People came up with was that winds are much stronger during glacial boundary conditions because of the ice sheets can help channel winds. So it's maybe a time that you have really, really strong winds just causing constant like divergence. Like it's just constantly driving the surface waters away and leaving like a sea surface low that like then deep waters would be coming up from underneath. So that's their hypothesis, and it sort of also explains why it went away, like why it was such a short-term event. Once the ice sheets melted, those winds can't be there anymore. Yeah. It seems like you had to hit like a sweet spot between like a little bit of deglaciation, changing something about the system, while the winds were still strong enough to kind of cause upwelling. And then once the ice sheets melted, the winds aren't strong enough anymore, and we switched to a different system.
Can it be melted during this period?
I mean, no, there's still ice now. Yeah, but what's considered a real ice sheet is gone in those meltwater pulse events by the end of
How does it look then when you look at the younger dries?
Which thing?
Because
The
it
younger dries.
switch back, right?
Right. Yeah, and it sort of does. I mean, the younger dryas is right in here.
Right.
So it's like an event here, a sort of return to almost glacial-like conditions, and then it looks like in my record, whoops, I just have extra data on here. The pre-boreal, it really only looked like the bullying Alrod really briefly, like only in the first couple of years, and then it couldn't really sustain it the same way.
Thanks.
No, I would, that question, what Rob just said, made me wonder about, like, in the younger dryas in the North Atlantic, where it's sort of like creating more stratified water.
Yeah.
And so I was wondering, right, like, I'm wondering if you would then be able to test that hypothesis in the North Atlantic.
There's a sort of theory that when North Atlantic water formation, deep water formation is getting shut down, maybe the Pacific takes up the slack. It's kind of, there's no physics to support why that would happen. Like it's really unexplainable, but we just keep finding it in a lot of records. So that kind of goes back to like the physical models just aren't capturing what we seem to be seeing in our data. Yeah, whenever the North Atlantic deep water gets shut down, the Pacific circulation changes way too rapidly for what you would think. So yeah, it does seem to have like a bit of a back and forth, but we don't really know why.
Yeah, and I was also just wondering, my question before, until Rob asked that, but my question before was if if that, what you see in terms of the pulses is all just driven by those strong, the strong deep water currents in the Atlantic. You have that big deep ocean circulation.
Yeah.
So just to like contrast it, I was just like,
I just like rushed my conclusion at the end, but totally. It just seems like what this suggests is that the diatoms aren't controlling the show here at all. They're really just passively responding to some huger change in ocean circulation. Sad for me, I thought the diatoms were going to be controlling everything in this story, but no, it really seems like they're just recording like some way more global and deeper changes in intermediate water and deep mixing that we just don't have a good handle on yet. Yeah. Should we switch to
Michelle?
Yeah, just like, so with upwelling, I mean, I'm imagining it's not just silica that would come out. Could some of the iron or other nutrients be coming from the silica or the upwelling? Yeah,
so certainly nitrogen would be coming with the silica, and phosphorus, those are usually all found together. Iron is a little bit of a harder one because it precipitates out of seawater just so rapidly that if there's deep water that's sitting there being really deep and old, it might just not have that much iron left in it. It would all get reduced away. So it's not really considered a source of iron if it's deep water. But there is some. There's absolutely some, for sure. Yeah. Okay.
At the point of the major glaciation, did we not have a source of a tremendous amount of dust that these high winds could have transported to the ocean and provided both silica and iron?
Oh, interesting. I don't think dust is considered a major source of silica to the region. There's a lot more that's just in the
Depends
ocean.
on the rock that's ground up to make it.
Yeah, I guess so. Yeah.
Because all of that seems to fit about the time at the major glaciation where they're grinding up all this rock and delivering into dust.
Yeah. I see what you're saying. It's definitely possible, and it's really hard to quantify how much silica might have been coming from glaciers melting, in fact. So not just dust from the atmosphere, but dust that's like suspended in that meltwater. That's something I'm working on trying to quantify for when I put it in my paper. The dust has been quantified a little bit by that other paper. I don't think dust alone is a source of silica as much as what's in the water, but it probably would be some. Yeah.
So if I understand your feedbacks correctly, I'm not wrong, but so during sort of when you're coming out of a glacial, it's quite windy, right? And that drives upwelling of deep waters to the surface.
Yeah.
And according to your data, you're showing that that is bringing up silica, which is increasing productivity.
Yeah.
Right?
Yeah.
And so that then drives the biological carbon bond, right?
Yeah,
And so then that should actually draw down CO2 out of the atmosphere.
should.
So how does one get out of an ice age? Is it just, I mean, I think you were kind of alluding to this a little bit, that like essentially the diatoms are along for the ride, or are they just not drawing down enough CO2 and it's too strongly driven by Milankovitch cycles, or?
I mean, this is just one spot in the ocean, but if we believe this guy's interpretation, no matter how much carbon got drawn out here, the CO2 escaping to the atmosphere was way more. I mean, that's his main conclusion. But you have to add it up every place in the ocean to get the full answer, right?
And that source of that CO2 is from deeper waters that are coming up, or?
Yeah, that's the whole idea with this. But this is just for the North Pacific. But I mean, there's a lot of CO2 that went into the atmosphere during this time period that we haven't accounted for. Where in the ocean did it pop out and enter the atmosphere from? So the subarctic North Pacific is like a candidate for that. Yeah. Okay.
With the decay of all of this, I'd say algae,
Mhm.
all the decay, do we have a methane event here?
Not really. I think most of it gets buried as organic carbon and stays in the sediment.
There's no the decay producing the hydrogen to have CH4.
It might be possible, but I don't know that that's like the most common way that the carbon goes. Yeah.
Because that's really a warmer upper.
Yeah, it is. I think methane is thought to be a different option other than CO2, but it would probably be from like permafrost melting or something, and not from this region.
I would assume somebody must have looked at volcanic input for these nutrient sources, iron sources, silica sources.
Yeah.
That's been looked at.
Yeah, so that's like kind of why I showed this at the beginning.
Okay.
Like this is someone else's paper, but they did either volcanic or lowest dust. I mean, it's not exactly at my same spot, but it's sort of considered to be a spot representative of the region. Part of the problem with iron, like I was kind of saying, is it's not always in a sedimentary form.
Right.
Sometimes it's in these kinds of invisible to the sedimentary record forms, like colloidal in the water, or like in a chelated compound or something. So you can go and measure how much iron got delivered in dust, but if there's iron coming from continental shelves, it wouldn't be picked up by this. It would be in some kind of weird, like a colloid probably. Yeah.
I would just add on the silica that most of that's probably hard to access by the diatoms because it is in the quartz, right? Coming into the shells.
Yeah, it definitely depends on how finely ground up is the silica. So a glacier can powder rock to really, really fine silica, fine enough that it does enter a dissolved form in the ocean. But it's really not clear and not that well studied, like how far from a glacier does that silica ever go? Most of it's going to just fall out as sand and silt and clay, but a little bit of it might go into this.
Yeah,
dissolved.
If it was not in solid form, right, it would go further, but the clays go further because they're flat.
Yeah. But it just takes a long time for silica to dissolve off of clay. So it's like a race, like could it dissolve faster? Would it sink out faster?
Yeah. I was wondering, like, I mean, you're well above the CCD. You're not in waters that are so deep, it's going to be acidic and liberating silica that ends up well and available to a diatom because it's in the right form chemically for it to make a show.
Okay, well, the CCD really only matters for calcite.
Right.
And silica, it actually goes the other way. So the more acidic the waters, the more silica it preserves. So
Right.
it's actually the opposite.
No, what I was getting at is that at some depth, there's an increase in acidity even beyond what gets rid of calcite, the CCD, to liberate silica from clays.
Oh, I see. Right.
So
Yeah.
now they're available for biological organisms.
Oh.
I'll take it and make an open shell.
Oh, yeah, maybe. Okay, that's a little out of my depth.
Just,
Yeah.
I'm just thinking out loud.
Yeah. I just don't know how fast those processes work. Yeah.
At the surface water interface is pretty fast probably. But I don't know either. I'm not an expert on silica liberation.
Mm-hmm.
In
Yeah.
acidic ocean waters.
Mm-hmm. Yeah.
Why don't we have back up your last question, unless someone's got a burning one, just because.
Oh, I don't have a question.
Or,
I just was wondering if there's any, before we wrap up here, if there's any community-wide announcements or anything that, anybody wanted to say what was happening around here in Block Hall and beyond, any cool things there? Anything, Michelle?
We just had a test today, I'm still in test.
I think so.